Hi, Tintin. Welcome back. Hello, John. Welcome back. Hey, Santino. Good morning. Welcome back. Hey, Jumila. Good morning. Welcome back. Hey, Zin. Good morning. Welcome back. Hi, Kim. Welcome. Good morning, Nidal. Hey, Irvin. Good morning. Welcome back. Hello, Jordan. Good morning. Welcome back. Hi, Bellman. Hope you're doing well. Hello, Faith. Good morning. All right, John. Thanks for letting me know. Joey G. Good morning. Welcome. Hi, Asim. Good morning. Hello, Kai. Hello, Nadina. Welcome. Joseph. Good morning. Welcome back. Hey, Tristan. Welcome back. Hi, Micaiah. Hope you're doing well. Hi, Mike. Welcome back, Michael. Hello, Wendy. Hey, Emma. Hope you're doing well. Hey, Ryan. Welcome back, Ryan. Alan, welcome back. Hopefully you had a good day off in that snow. Hello, Philip. Hello, Leonardo. Okay, just looking for Frank and Alex Gregory. Alex. I'm sorry. Hey, Frank. Welcome back. All right. Good morning. Welcome back. I hope you guys are all doing well. I'm looking for Greg or Alex. If you're here, please let me know. All right. Hopefully you had a good day off from chem class yesterday. They got a lot of snow. No snow day. That's okay. We're home. It's a virtual world anyways. You guys have technology, have all the devices that we need to operate. So I guess you didn't have a snow day. All right, so let's check out the COVID report for the last couple of days, see where we're at in the county. So the Oneida County COVID report, here's the dashboard. Some good news here. So hopefully you remember some of the values that were up here before. Last time we saw this, there was over 3,000 cases that were still active in the county. Right now, there's 15,246 that are resolved in the county. So we got rid of a lot of cases, or a lot of them have been resolved. Yes, 350 of them out of the 15,000 were deaths. And I'm assuming everybody else is either in the hospital or probably not in the hospital if it's resolved. Probably all through with COVID. So I don't know the criteria of being resolved. I don't know if it's maybe they still have complications in the hospital, maybe not. Maybe they don't have any COVID in their system. But from my understanding, once you're diagnosed with COVID, it's in your system for a long time period. So I'm not sure the criteria of that. But yeah, 350 people or 350 different families have been affected by COVID. Maybe it's not someone directly in your family that is close to you, but you probably, maybe, know somebody that has passed away from COVID or someone that might be really sick. Hey, Alex, I hope not, but so think about all the people that are affected there. There's 118 people that are in the hospital still, and there's still 21 people in ICU. So those numbers have decreased too. Let's check out the number of daily positive cases. So check out that curve. This is the number of daily positive diagnostic testing. That second curve looks pretty darn good. It's starting to look good now. Not a couple weeks ago, it didn't look very good. But right now, it's starting to form into a nice curve. It's starting to flatten out, or it's definitely in the downward slope from analyzing it from this perspective. So if you go check it out a little closer, let's just check out some data last couple days. Looks like last data looks really good. Looks like there's like nothing there, but there is some still. It's just there's a high point relatively close. Yeah, there's 51 cases. That's amazing. Ever since like September, I've been going through this. I've been telling you the number of cases and back to 51 again. So after like, we'll say Halloween, then it started getting crazy. But now we're back down to 51 cases. The day before was 61, and the day before that was 64. So those numbers are really good in comparison to a couple weeks ago. The day before that, on the 29th, there was 141. So that was a little bit of a spike in comparison to the previous day, which was 71. So those number of cases continues, looks like it's decreasing pretty good. If we continue decreasing at this rate, I think we'll be getting closer to normal again. So I think if it continues at this rate, I don't know what's going on with school. I don't know if it's planned for us to go back to school this year. I don't know any of those details, but as soon as I do know, I will definitely let you know. But those last data, that 51, last time we had a day of 51 or less was the 22nd. 22nd was 34. The day before it's 47. So like all pre-Thanksgiving. So middle of November, we had some data that was similar to that. I'm checking out this curve. I'm looking at that slope at the end of it. Let's check it out again. So what's going on the last couple weeks? Oh, that's a little high. Last couple of days. Yeah, a little high on all this stuff, but you can see that. What mimics or the reflection of that looks like it might be, I don't know, something similar to that. So hopefully we continue this process of decreasing. If we continue that pattern right there, which I would assume we will, if we continue that pattern, then it's going to be like odd days of maybe 3 cases, 10 cases, maybe 20 cases some days. It's going to look like the first wave. And I would bet if we see numbers like this again, if we see numbers like the first wave all the way up to that point, I think things will get pretty much back to normal around here. Not taking her mask off, but still practicing social distancing and all that stuff. But if we mimic these numbers again, I would assume that we'd be back in action. Hopefully. I want to actually get to know you guys, say, hey, put a name with a face. I see a lot of blacked out screens, which is okay because I know what it's like on the other end. I've been there. You don't want to show off your background all the time, like my pink background. I just love showing it off to you guys. So that's why I do it. And it's a little bit different. All right. So anyways, there's a COVID report for today. Let's go through, figure out what the heck's going on for class today. So hopefully, again, you had a good day off. Hopefully you shoveled your tails off, got a good workout in. So welcome back. The quote of the week comes from Colin Powell. There's no secrets to success. It is a result of preparation, hard work, and learning from your failures. So make sure you set those goals, prepare for those goals, put the work in, and learn from the mistakes that you have. Either it's this class, maybe it's math class, maybe it's your college journey. Maybe you're preparing for college and you have to work a little harder. But make sure you learn from mistakes. All right, the daily agenda for February 3rd, 2021. Today's a day 4. Continuing on with Unit 6, Properties of Solution. We are going through topic 2B. There's going to be a lot of notes on this, and we'll analyze examples on this as well. There's a YouTube flick we'll start off with, then we'll get to some guided notes, another flick, and then we'll probably get through like a handful of examples today. So next class, we'll go through more examples, and then I actually will give you time to work on the exit pass as well. So you have 2 days, we have 2 classes, 2 more classes to analyze this chart and to really figure this chart out inside and out. So that's the goal for today and a sneak peek of what's going on for tomorrow as well. Start off with this flick on solubility curves. There you go. More information about solubility curves.
We have learned about the solubility rules in a different lesson. These rules help us predict whether or not a salt is soluble in water. For salts that are soluble in water, some are more soluble than others at a given temperature. In this lesson, we will learn about solubility curves, which is a graphical representation of the solubility of a certain salt over a temperature range. If we were to compare copper 2 sulfate and potassium sulfate, we will find that one is bright blue and the other is white. If we tried to dissolve them in water of equal temperature, we will find that copper 2 sulfate is a lot more soluble than potassium sulfate. In other words, copper 2 sulfate has a higher solubility in water. This is actually a physical property of a substance, much like a substance melting point and boiling point. The solubility of a salt is usually measured as grams of salt per, let's say, 100 grams of water. Here is a challenge for you. Do you think solubility increases or decreases with temperature? Pause, think, and continue when you have an answer. The answer is that solubility usually increases with increasing temperature. So, if we dissolved copper 2 sulfate and potassium sulfate in hotter water, we will find that more of each salt is able to dissolve. This observation is only applicable to a solid dissolving in a liquid. We can measure how much of a given salt can dissolve in 100 grams of water at a certain temperature. We can plot solubility as a function of temperature to give a solubility curve. Here are solubility curves for copper 2 sulfate and potassium sulfate. We can see that for all temperatures, copper 2 sulfate is more soluble than potassium sulfate. From a solubility curve, it is also possible to find solubility at a certain temperature. Let's say we wanted to find the solubility of copper 2 sulfate at 90 degrees Celsius. Take a ruler and draw a vertical line starting at the x-axis at 90 degrees Celsius until it reaches the curve. Then, draw a horizontal line from the point on the curve until it reaches the y-axis. At 90 degrees Celsius, approximately 68 grams of copper 2 sulfate is soluble in 100 grams of water. To compare, at the same temperature, only 24 grams of potassium sulfate would be soluble in water. Using the provided graph, try to find the solubility of potassium sulfate at 60 degrees Celsius. Pause, try, and continue when ready. If your answer is around 18 grams of potassium sulfate per 100 grams of water, then you would be correct. When a maximum amount of a certain salt is fully dissolved, the resulting solution is known as a saturated solution. In a saturated solution, no more solute is able to dissolve. If we took this saturated solution and let it cool, it would become a supersaturated solution. This means that there is more solute than the maximum amount able to dissolve. When this happens, some of the solute may crystallize or come out of solution.
All right, so there's a little bit more information on what's going to happen for today and solubility curves for today's class as well. All right, so next up, let's open up our guide notes. So there's no warm-up today. We'll save that for examples at the end. So please open up your guided notes, Unit 6, Properties of Solutions. I don't think I have to keep going through this, but it's under classwork. It's under Unit 6. And then obviously you can find the assignment there as well. But just in case, scroll through the assignments. It's probably the first one listed. Guided notes, open it on up, and it should be your own document as well. It should be your own document. All right, so where we left off, we talked about solute, we talked about solvent, we talked about solutions, we talked about saturated, unsaturated, supersaturated. So all that stuff we talked about, I told you there's a lot of S terms within this unit. It's not a bad idea to make an index card to define each of these definitions. So last time we talked about, and I went off on a drawing spree for a second, just a refresher where we're at. Last time I talked about me going to Walmart, picking up a nice, fresh, brand new sponge. So there's my sponge, brand new, right out of the package. Boom. And we refer to the sponge in terms of saturated, unsaturated, and supersaturated. Told you about bacteria, about the sponge. Told you how I turn the sponge on. Got a little faucet up here. Throw some water. And probably like a stainless steel. Stainless steel is used because it doesn't really collect a lot of bacteria. So that's why it's used on a lot of surfaces, cooking surfaces, stainless steel. Bacteria doesn't strive on that surface. All right, so there's my faucet. And we talked about this in terms of like water being turned on. So right now I have a brand new sponge. Let me put some little sacks right here. So the sponge could absorb some water. Got a sponge at home. You know exactly what I'm talking about. You should definitely know what these terms are in reference to a sponge at least. But I think this is the best way to start off the convo on saturated, unsaturated. All right, so I put the water on and all right, the water's on, and so what's going to happen? Water is going to flow on down, and obviously some of the water is going to be absorbed. We're going to say all the water is going to be absorbed into the sponge for now. So yeah, I have like these little water droplets being absorbed within the sponge, and now I'm going to shut that water off. Turn that water off. So at this point where there's still more room for more water to be absorbed in there, this is called unsaturated. So point right here, this is called unsaturated. There's more room. So if you look at the term for unsaturated below, I think 5 screens in the way. Unsaturated, there's more solute or more water can dissolve. More water can dissolve within the solution. Yeah, it's also true for clouds. So there's a cloud forming. Water droplets are forming in the cloud. So water droplets are forming within the cloud. There's more room for water droplets there. It's not completely full. It's not going to rain yet. So this is unsaturated in both situations. Next up, let's put that water back on. The water back on. So this is unsaturated. There's more room for water. There's more room for solute to dissolve. All right, so the water's flowing again, getting it rolling through. More water is back on. And now we're going to get to the point where the water, there's just tons of water. Got to pick up this mess. Now let's cover this whole sponge with water droplets. There's no more room for any water here. There's no more room in the cloud either. So the cloud absorbs more water vapor. Both of them have a maximum amount. All right, so let's check it out again. So at this point, turn the water off. We're making a big mess all over the place. Turn that water off. All right, so I turned the water off, and the sponge over here to the right, there is no more like yellow sacks available for water to absorb within it. So if you press the sponge, it's going to be really firm and full of water, heavy as well. Same thing with the cloud. If cloud, touch that cloud, poke it, maybe a drop of water come out. But anyways, just joking on the cloud. But the cloud is full of water. It's saturated. It's at the maximum amount of solute or the maximum amount of water within the sponge or within that cloud. So they're full. No more room for any more water to absorb. So that is saturated. There's no more room for anything to go absorb. It's at equilibrium. Why is it equilibrium? So saturated is also referred to equilibrium. If you add one more drop of water, it's going to flow over. If you can't take any more water in, you can't take any out, it's saturated, it's full, it's at equilibrium. So same thing for the cloud. Let's throw that water on one more time here. So put the water back on. Faucet is now rolling on. And I'm just going to take one drop this time. just one drop. So I'll put one drop onto the sponge. There's my one drop. Looks make it a little bit bigger. So that one drop falls onto the sponge. Probably do a different color, different blue. My one drop hits the sponge. What's going to happen? It's going to reflect and fall right off. I put another drop onto the sponge. Right there. It's going to hit it and it's going to bounce back off. So no matter how much water you put onto the sponge at this point, it's all going to just seep on over to the edge. It's not absorbing anymore. If I take another vapor, water vapor, and put it to the cloud, what's going to happen? That one droplet is going to fall in the form of rain. So at this point, you add more water, you're going to have some water falling out. You can't take any more in. This is called supersaturated. More solute was dissolved than what will dissolve. So you can't dissolve anything else. It's completely full. And that's the type of example we left off with last time. Unsaturated means it can take more in. Saturated means it's at its maximum potential. You can't take any more in. And supersaturated means it's just going to flow right on over. There's way too many particles. Supersaturated means you're going to see like salts in a solution. If you have a beaker, if you have water in there, you're going to have like solid particles present. It's going to be a heterogeneous mixture. An unsaturated and saturated would be a homogeneous mixture as well. So here we go. Let's get to our notes, figure out what we're going to do today. There's drawing with Mr. Brown again. All right, so we are going to finish up concentration and solution. Just a little heads up where we're going to be today. We're going to do a bunch of notes first. Concentration and solution, solubility curves, solubility tables, and then we'll highlight a couple portions of this chart as well. So that's our goal for today, at least for notes. So here we go. Pull this up. It's concentration of solutions. Since our solutions are going to be a homogeneous mixture. It's going to be obviously a liquid that we're analyzing now. It could be solids, but solutions are going to be a homogeneous mixture. They're going to be aqueous. Homogeneous mixtures, their components can vary. Components can vary. So what I mean by this, if we're talking about a homogeneous solution of lemonade, we're making lemonade. Maybe you made lemonade before, maybe you made Kool-Aid before, whatever you're talking about. Making lemonade, maybe Mr. Brown doesn't like a lot of sugar in his lemonade. Maybe you like a lot of sugar in your lemonade. Maybe you like it a little sweet. Maybe you like it a little sour. So the amount of sugar you add could vary. So homogeneous mixtures, the amount of solute or components can vary. Often you can refer to a solution as dilute, or concentrated. Dilute or concentrated. And what does dilute mean? Dilute means there's more water in there. It's more watered down. If your Kool-Aid is diluted, there's a lot of water in there. If it's concentrated, that means there's going to be more solutes, or you're going to have a lot of taste to it for the Kool-Aid or lemonade, whatever you're talking about. Usually think about drinks for this situation. The term diluted, dilute is having a relatively low concentration, So if something's diluted, my lemonade is diluted, it's low concentration means you're not going to really taste the lemon or the sugar too much. Low concentration. So diluted, low concentration of the solutes. So what you'd add to it. Maybe there's not much sugar. Maybe there's not much lemon. To make lemonade, all you need is water, lemon juice, and sugar. Classic lemonade. Maybe there's not much lemon juice. Maybe there's not much sugar, whatever it may be. Solute in the mixture. Something's diluted, low concentration of solute. Growing up, we're a family of 4. Mom and dad didn't have much money, and what mom did all the time is she diluted our Kool-Aid all the time. Like Kool-Aid all the time was diluted. Tasting it, I didn't think much of it. It was Kool-Aid to me. It was watered down. I didn't really realize the difference until I went to my friend's house and I had like the same Kool-Aid, and I'm like tasted their Kool-Aid, and it was like so sweet and like powerful, and you could taste like all the flavors exploding in your mouth. I'm like, what the heck's the difference? I didn't realize it until I was older. I'm like, hey mom, the Kool-Aid tastes different over there. It was more concentrated. They weren't trying to stretch it. My mom like always tried to stretch like the dollar as far as it could go, and try to stretch out the Kool-Aid as far as it could go. So we always had diluted Kool-Aid, which is okay because they had like less calories, less sugar. But how's your Kool-Aid? Things you do to save a few bucks. It's okay. All right, concentrated. Something's concentrated, like my friend's house, they had some concentrated Kool-Aid because they were, those type of people, I guess, which is okay. Low amount. I'm sorry, not low. Having a relatively high amount of solute present in a unit of a mixture. So very similar. That's the opposite of dilute. Dilute, concentration, concentrated. Maybe like your Gatorade, like really concentrated. Or maybe like the Powerade Zeros or whatever. It's not as concentrated. It doesn't taste as sweet usually. All right, determine the solubility. Next up, solubility. Determine the solubility. Solubility information is presented in different ways. The solubility curve on the reference table, it's page 3, presents quantitative information. Quantitative. Quantitative, we saw this earlier. Quant, you see quantity. Quantitative information is going to have a numerical value expressed with the information. Shows a relationship in grams of solute that may be dissolved at various temperatures. So all this information is just analyzing or interpreting the x and the y axes of the graph on page 3 at various temperatures. The relationship, grams of solute. So how much solute you add when you make your Kool-Aid, lemonade, that how much Kool-Aid powder will dissolve basically at different temperatures. Yeah, the factors, the numbers will be different when temperature changes. So if you ever made iced coffee or, I don't know, iced coffee versus hot coffee. So maybe you work at Dunkin', maybe you will work at Dunkin', maybe your mom gets a Dunkin' iced coffee and you watch them shake it on up. If you ever just make hot coffee and you dump some sugar into the hot coffee, the coffee's hot, you dump the sugar in, you swirl it around a few times and it's dissolved, easy. If you make iced coffee, it's a colder temp. You put the ice in, you put the coffee in, put the caramel, whatever you put in with it. But then you put the sugar in, and then you're like, oh, shake that thing up. They take the cup and they keep shaking it on up because the sugar is not dissolving as quick as it would in hot temperature. So really, temperature does have a factor. Temperature does affect the rate of reactions. The colder the temp, the longer it's going to take to dissolve. So temperature does play with dissolving rates. We'll talk about that next units with kinetics. The solubility curve is a table that shows the grams of substance. Grams of substance. Several different things. The common ones are going to be on this table. Yeah, it is intimidating because there's a lot of information there, but it's not hard. After a little practice. That can dissolve. And it's going to be out of 100 grams of water. 100 grams of water at temperatures that range from 0 to 100 degrees Celsius. So they're just going to be within the range of 0 to 100 degrees Celsius. On this chart on page 3, each line or each curve, and you don't have to color code it. You don't have to change the text, just the style font. On that curve, each line represents the maximum amount. It's wrong. Of a substance that can be dissolved. So the line represents the maximum amount of a substance that can be dissolved. At a given temp. Given temperatures. And we'll see a ton of examples. This is called the point of saturation. So once you're done with that, I'm just going to put equals saturation, or the point of equilibrium. So the line represents saturation or the point of equilibrium. The lines on the curve. So on page 3, hopefully you have that handy. At this point in the class or the year, I'd probably print out like 10 different copies, 10 different charts. And I'd pass them out to you guys so you can mark them up. So if you have access to a printer, I'd print out a few copies of at least this table. If you don't have a printer, then you have to be creative. You're going to have to figure out a way to really mark up this maybe on the computer. I will use Zoom Annotate quite often with that, and you'll see that, but you have to be able to do it as well. Think of a way, maybe you want to use just a paper, a pencil on the chart and just erase after every time. That's not a bad idea. But let's get back to this. Here we go. All the lines of the curve that show an increase in solubility as the temperature increases represents solids or ionic bonds. So the ones that represent an increase, the ones that are increasing are going to be either solids or ionic bonds, same thing, solids and ionic bonds. Temperature increases, and we'll highlight this in a few minutes. Solids or ionic bonds. Ionic bonds are metal and non-metal, we know that. And they're being dissolved in water. So all of these are actually being dissolved in water. Solids or ionic bonds being dissolved in water. Water, great solvent. Most common solvent. Within this, there's 3 lines showing a decrease as temperature increases. The 3 lines that show a decrease are going to actually be covalent bonds, or they're also going to be gases. Covalent or gases. Gases, covalent. So covalent bonds again are 2 nonmetals. So nothing to write down here. I just want to go through these. I want to just compare those numbers that are increasing, or the values that are increases versus the ones that are decreasing. All right, so I'm just going to highlight some lines here. You don't have to highlight it, but I just want to look at, make sure I'm correct with this. So here we go. I'm going to analyze this one right here. The ones that are increasing. So the first one's increasing, Ki, metal, and a nonmetal. The second one that's increasing is NaNO3. It's a polyatomic ion. It's a ternary compound. So that is definitely increasing. Next one I see is KNO3. So I'm going to follow that on up. It's pretty steep slope there. They're not going to ask you to find the slope of these, but you could do that if you really wanted to. That's increasing. Next one, NH4, that's increasing. This is the only exception of an ionic bond, but it's still a solid at STP. Another one that's increasing, not as steep, is KCl. NaCl is increasing very slowly. And last one's KClO3, increasing. So all the ones in yellow on this chart to the left are increasing. Those are solids being dissolved with obviously a liquid of water. Most of those are ionic bonds as well. Let's check out the gases. There's only 3 of them. First gas or covalent bond, I have HCl, it's hydrochloric acid. It's pink, it's definitely decreasing. We have NH3, covalent bond, gas, definitely decreasing as well. And SO2, covalent bond, this guy is decreasing too. So when they ask you a question on this chart, they're going to ask you about maybe just one specific ionic compound, one specific chart, one specific line. They're not going to ask you about every single one of them. They might ask you a question about KNO3, and everything else will be like garbage. It's just there to screw with you or just mess you up. There's extra information behind there to just to throw you off. But we'll show you how to interpret that. But yeah, again, the yellows represent ionic compounds. They're solids at STP. The purples would represent gases or covalent bonds. We'll check that out. More on solubility guidelines. Solubility guidelines. Guidelines for solubility of common. So these are guidelines for most ionic, for the common, I should say, ionic compounds. Is every one up here for ionic compounds? No, but these are the most common, the most typical ones that you'd analyze in class. When we get back to class, hopefully sooner rather than later, we'll actually do a lab on analyzing the solubility at different temperatures of salt. These tables are useful for predicting whether or not a solid will form. It's also called precipitate. Precipitate, not precipitation. Precipitate. Precipitate. Either way. Precipitate. Precipitate. There's a couple different ways you could say that one. Precipitate. Precipitate. Spelled wrong. Better. And all that means is when a solid forms. So precipitate. Precipitate. Precipitant. When the ionic solids of a solution are mixed. So what does that mean? That means when you have a solution of salt water, let's say take salt water, draw on a beaker here. Images are, I think you can see my images. Having fun with them still. All right, so there's a beaker or a pitcher, I don't care, something that you can measure a volume with. Inside that beaker is going to be obviously water. So I'm going to throw some water in there. Water. Inside that beaker is 100 milliliters of water. So we're going to have 100 milliliters of water. Whoops. Milliliters. And we should know 100 milliliters is also equal to 100 grams of water. The conversion for milliliters to grams of water is 1 milliliter equals 1 gram of water. So for 1 milliliter of water in a graduated cylinder, it equals 1 gram of water. It's not true for every liquid. 1 gram is not always equal to 1 milliliter, but for water, the unit conversion is going to be that. It's always 1 milliliter equals 1 gram of water. You can do the math on it, and again, I would have done this lab earlier with you where you could actually saw the difference, or how 1 milliliter is equal to 1 gram of water. But anyways, there's 100 milliliters of water. And get rid of that now. So it's full of 100 milliliters. And if I took a sample of table salt, if I weighed it on like a weighing boat on a digital scale, let's do that quick. So there's a scale, digital scale, gives you a measurement down here. I'm going to start off, before I put the stuff on the scale, I'm going to press the tare button. So there's a tare button or a zero out button. And that zero out button allows this to be 0.000. So I want to read 0.00 grams before you start it. If it doesn't say 0.0 grams, then you have to press the tare button just to start off with a tare. Start off with nothing on the scale. So sometimes there'll be like little salt crystals or something on there that you don't want to touch. So instead of touching those things and getting them off the scale, you just press tare, and it starts off with a clear scale. So next up, I'm going to put a weighing boat on there. So let's put a weighing boat on there. It's just like a little dish, little bowl. It's not going to be green. It's going to be like light white. Just a weighing boat. And you just put chemicals in there. It's plastic, like a little solo cup or something. You throw it away when you're done with it. But anyways, if I put, I don't know, let's put some salt in there. Put some brown salt. If I put some, okay, before I put that salt in there, it's going to read a measurement of like, I don't know, maybe 1.2. Once that's on with nothing, you're going to press tare again, because I want 5 grams of salt. I don't want 5 grams plus the weighing boat. I want just 5 grams. So I press tare again, and it reads 0.0 again. Once I put some salt on there, it's going to read 1 gram, 2 gram, 3 gram, 4 grams, 5 grams. If I put 5 grams on there, now it's 5 grams, I'm going to take that solute, NaCl, and add it to the solution. This is out of 100 grams of water. I'm going to take those 5 grams, add it to the water, and they dissolve. If they all dissolve, I stir it on up and they all dissolve, then it's going to be unsaturated. If I add another 5 grams, put it back in there, dissolves, stir it on up, and they all dissolve again, it's still unsaturated. If I take another 5 and add it again, and I stir it on up, and I start to have some solids present there, that's called your precipitate. A solid's going to form on the bottom. It went from a homogeneous mixture to now a heterogeneous mixture. If I had 5 more grams, it's not going to dissolve. You're having more solids forming. It's probably going to settle on the bottom once I'm done mixing it out. So that's going to be a solid forms present on the bottom. And that's this type of stuff we're talking about with this curve, adding solutes to a solution. All right, let's finish it up. Next up, a reaction will take place for one or both of the products listed as insoluble. Insoluble. I think that's it for the actual note portion. Yes. Now let's analyze that chart a little bit. Insoluble is last thing. All right, moving on forward, we have this chart right here. So I would give you highlighters at this point and we'll mark it up, but it's not gonna work out that way. So what I'm gonna ask you to do is click on the image, cut that image out by hitting, there should be a blue box around it. Cut it out by hitting Control X or right click your mouse, cut, or you could 2 fingers down your Chromebook, gives you this, cut that out. And what we're going to do, we're going to add that to a drawing page. So I'm going to add insert, drawing, new. And I'm going to paste this little diagram, which is on page 3, this chart graph, right to this as well. What we're going to do, we're going to mark it up. We're going to put some basic notes here. Yes, I'm going to ask that you please do mark it up like mine as well, or similar to mine. Does anybody need to see what I just did there for the steps? All right, so now what we're gonna do is I'm gonna go to my little line segments, and what I'm gonna do, I'm gonna identify all the solids or ionic bonds, and we'll identify the covalent bonds or the gases. So I'm gonna go to line. You can use a line or you can use a scribble feature on the bottom. I'm using line. And with the line segment, I'm going to highlight the ones that are increasing, the ionic bonds. So again, just kind of mock or just go over mimic the ones that are increasing. It's a black line, so I'm going to change the color to whatever color you want. I don't care. I'm also going to change my density, the thickness of that one time. If you do that one time, everything else that you have, as long as you're in that feature, will stay that color and that density. So there's the first one. If it's a straight line, it's really easy to do. If it's curved a little bit, you're just going to put several segments throughout. So yeah, I don't care if you did one straight line for the next one. But KNO3, you're probably going to have to do several segments there. So starting, I don't know, I start from the bottom, but if you scribble, if you're better with that, you're more than welcome to just trace that line. But anyways, these all represent an increase in temp. As temp increases, the solubility is going to increase as well. So when you add more solute, it's going to dissolve. These lines here, the lines all represent a point of saturation at a given temp and in terms of solubility. How much solute you add. Probably still a little confused with this topic, but again, once we get through the examples, you will definitely understand it. So KCl, easy to draw that one, just one straight line. Same thing for NaCl, table salt, sodium chloride. Again, these are the most common types of ionic bonds or covalent bonds that you'll analyze. They're not going to ask you about anything else besides these on the reagents, any one of these on the reagents. And yes, I really still hope you have the reagents. I think if you're doing the work, you guys still will, see John, you guys still will do pretty well. Labs, there's no practical. You're just missing that experience a little bit. All right, so go through, highlight all the ones that are increasing. Once you're done with that, I'm making a little key over here to the right. I'm gonna call that obviously ionic bonds or ionic bonds or solids at STP. Ionic bonds or solids. How am I gonna do that? I'm gonna add a text box here. And I will give you time in a few minutes to copy this down. So the yellow lines, or whatever color you chose to use, are ionic bonds or solids. That's my first key. Again, you're going to do the exact same thing for the covalent bonds or the gases. So there's only 3 of them. I'm going to pick pink again. You can pick any color you'd like. But again, change the density, make it a little thicker so it pops out at you. My scribbles on here does not work out very well. That's why I do segments. Just connect those points, plot those points, connect those points. All right, so there's only 3 pink lines. There's 3 covalent bonds. I know some of us work a little quicker than others. So the pink, I'm gonna put a text box there again. represents covalent bonds or gases. I'll give you a couple minutes to copy that down. Okay, hopefully that's enough time to at least get what we have there. I do want to add 3 more text boxes. I add one at a time, and the 3 text boxes are going to highlight the terms that we talked about in the beginning of class, like unsaturated. First one is unsaturated. If a reference point is under the curve, it's going to be unsaturated. So we'll talk about that real soon. A point is under the curve, under, unsaturated, under a curve, it's called unsaturated. Unsaturated point is going to be under the curve. Unsaturated, under. Next one, if the point is on the curve, it's going to be called saturated. This would be like a good little key to refer back to if you need to. If something's saturated, its point's going to be on the curve. It's also called at equilibrium. So any point on the curve, reference points on the curve, it's going to be saturated or at equilibrium. The last one, if a point's above a curve, last text box, this is called supersaturated. So I started off today's class talking about that sponge. We'll wrap up today's class talking about these terms, saturated, unsaturated, supersaturated, in terms of solubility or how much solute you add to the solution. Same type of idea. Supersaturated is going to be a point above the curve. Point above the curve. Super, all the way at top. Saturated in the middle, on the curve, unsaturated below the curve. And that's going to be it for notes for today. But you may want to refer to this when we get through those 5 examples. So I have 5 more examples to go through. And that'll be a wrap. All right, once you know that, you could save it and close it. And what I would do is I'd make this thing that we just created here like a whole page if you can. So I'm going to wrap my text and I'm just going to make this as large as I can. Try to make it like a whole page if you could. It might be a little bit distorted, but Make it as large as you can. If you look at page 3 in the reference table, that chart is the entire page. So that's going to be, try to make it as big as possible. Gives you a lot of information about it. Should have done this before. One more thing I'm going to do, I'm going to just take this blank table. I'm going to take this table and find it online. I'm going to paste it below so you have a fresh copy without like this extra stuff in there as well. So I would suggest doing this. You don't have to do this. I'm not going to penalize you if you don't do this, but I would definitely suggest making and finding a blank copy of this table and pasting it on another page, kind of like what was there before. So I should have copied and pasted right from the get-go, but I didn't. So anyways, once you're done with that, I would go to a new file, pop up a new file. Okay, take this page? No. Jerk. So rude of me. All right, so what I'm going to type in is New York State Regents Chemistry Solubility Curve. There you go. New York State Regents Chemistry Solubility Curve. Type that in the toolbar. I'm going to go to Images. Oh, if you need more help with that, you could watch these videos probably. And someone could help you out with that, but I'll help you too. That's what I'm here for. Just gonna pick any one of these solubility curves, one that looks similar to the reference table. I'm gonna copy it. I'll pull it back for a second. I'm gonna copy that image, copy image, and I'm gonna paste it right below the last one. Hopefully it pastes. Oh, it's cute, nice and small. I'm gonna blow it up. And then you can analyze this if, oof, not very clear, but analyze this if you need to. Image is a little foggy. A lot of times what happens there is if you double click on the image, it'll bring you to the main page of that image. Try it out. So click on the image. If you find it in the original text or the article, if you could download it. This won't let me download it. But a lot of times if you download it from here, it'll copy in a little bit clearer. Didn't work out for me. Try Kent. But you can leave the one you have there. Or you can put a couple in. You'll need them. Yeah, it looks like it's going to be a little bit clearer. So I picked the Kent chemistry one, went to the home page of where it was. It's not as blurry. But it's fine if you have the foggy one. All right, so now we're going to be analyzing this chart quite a bit. So it's not a ton of time, about 25 minutes left of class. We'll go through 5 examples. We'll do them together. And we'll figure out what this chart really means. Anybody need more time with anything? All right. So I'm going back to my home page. Go back to your stream, please. And we're going to wrap up with class. Oh, I guess I'll play a video quick. Let's watch a flick, then we'll go through examples.
For those about to dissolve, we salute you!
Nice. Great. Now we're going to get sued by AC/DC.
A salt dissolved in water in a beaker today. The ions broke apart in the usual way. The molecules of water kept the ions apart. A salt solution formed, but that's only the start. Homogeneous, the same throughout. Homogeneous, the same throughout. Solvents that are polar can dissolve solutes that are polar or ionic. That is really cute. Water and nonpolar solutes just won't mix, but a nonpolar solvent like benzene can fix. Like dissolves light, polar and polar. Like dissolves light, non-polar and non-polar. And all the solvent molecules used up and are stuck to the solute ions in your cup. Solution saturated, it is full for sure. Solubility's been reached for that temperature. Saturation on the line. Saturation on the line. If distill some water molecules unstuck, then more solute can dissolve. Hey, you're in luck. Solution is unsaturated, can't you see? You haven't yet reached the solubility. Unsaturated, put more in. Unsaturated, put more in. If you put more solute in than can be dissolved, then a supersaturation situation's involved. The excess falls out as a precipitate, or the solution is unstable sodium acetate. Supersaturation, precipitate. Supersaturation, precipitate. A salt dissolved in water in a beaker today. The ions broke apart in the usual way. They made it harder for the water to boil and freeze, so the fission temperature changed a few degrees. Colligative properties depend on concentration. Colligative properties depend on concentration.
Electrolytes have a greater effect on the melting and boiling point of the solution than non-electrolytes.
More solute that's dissolved got more effect. Solution's boiling point increases direct. The freezing point decreases, which is really nice. In the winter, salt on roads can prevent the ice. Add a solute, boiling point goes up. Add a solute, freezing point goes down. That is wicked cool. Solutions rule.
Solutions rule. That's right. So there's a little bit more insight on obviously solubility. Watch it again and again. I'm not gonna watch it though. All right, so last thing for today's class, let's go through a few examples. The examples are above Unit 6, Topic 2B, solubility curves. So what we don't finish now, we'll go through as a warm-up next time in class. All right, so you have the examples uploaded, nice solutions up on top, an Erlenmeyer flask, nice colorful solutions. And you also want the reference table, at least page 3 of the reference table. So I would have that handy. I don't care if you have the hard copy or a digital copy. Totally up to you. I want that table too. I'm not going to go in numerical order. I'm going to pick the easier questions first to analyze, and then we'll go through some more. So I'll do a few questions, and I'll have you guys wrap up at the end of class, and you guys will help me out with a couple questions. So I'm going to start off with actually question number 6. So starting off with question number 6. The question reads, so please find question number 6. I'm going to mark it up quite a bit. At 10 degrees Celsius, 23 grams of a substance saturates 100 grams of water. This substance could be what? So here we go. Just like we approach any question, figure out what the heck you have, figure out what it means, figure out what they're asking you to solve for, and then you could make an approach that way. So here we go. A couple things to analyze. We have 10 degrees Celsius. That's a temp. We have the next piece of data, which is 23 grams. That's a mass. And it says saturates. Maybe that means something to you or not. Maybe does. Should. Or it will. The substance that we have is going to be out of 100 grams of water. So if you see a question like this, hopefully you know you have to use the reference table, page 3. Doesn't tell you specifically you have to use page 3, but you have to. Sometimes it will say, hey, use table G, and they'll give you this information. The substance could be what? So I put a big red flag here because it says 100 grams of water. This chart to the left, a couple things to analyze. You have temperature, degrees Celsius from 0 to 100. We said it before. Said in the notes as well. And we have solubility per grams of solute, like 23 grams, per 100 grams of water. So why did I put a red flag over to the right in that question? Because it's not going to always be out of 100 grams of water. Right now, making it easy, it's out of 100 grams of water. Sometimes it'll be like out of 200 grams of water or 300 grams of water. When those conversions are not the same, when it's not in the question, when it's not 100 grams, then you're going to have to convert it. That'll be tomorrow's class. So you're going to have to convert that when it's not going to be the same value of 100 grams of water or 100 milliliters of water. But it's the same, so we check that off. It's easier to do this question. It's going to be right from the chart. All right, so now let's go back to the question. We have a 10 degrees Celsius. So find 10 degrees Celsius, mark it on up. Temperatures on the X. 10 degrees Celsius, make a line all the way to the top. All right, we have 23 grams of solute. Find 23 grams of solute. There's 20, there's 30. 23 is definitely less than the midpoint of that segment. Maybe it's a little low, but I'm going to go with it. So now that intersection point, I'm going to mark up. X's don't really pop in too well, so I'm going to put a heart, a little high, a little better where it should have been. That heart represents my intersection point. And another thing from the passage it said was point of saturation. The substance saturates 100 grams of water. So that heart indicates my reference point. It wants to know which one of these substances up here represents the saturation point. If you refer back to your notes, saturated is going to be the point where it's going to be on the curve. So points on the curve is saturation. So we're looking for which one of these is going to be on the curve. So let's find each one of these curves. I'll color code them. First one up, I'm going with NaNO3. Find NaNO3. Oh, there's NaNO3. Is that heart on the curve? No, not even close. That heart's below the curve. You see that heart's all the way at the bottom. It's under. In this situation, that would be called unsaturated. That heart's below the curve. It would be unsaturated. Now find the next one. Find KNO3. Find KNO3. There's a lot to analyze here. Find the KNO3. Oh, there's KNO3. KNO3. Following on up. Oh, that heart hits right in the middle of that curve. That heart is on the curve. That looks like it's going to be a saturated solution. So that looks like it might be a good choice. Let's keep analyzing more for practice. Let's find NH4Cl. NH4Cl. There's NH4Cl. I'm going to color code this curve. NH4Cl, nice straight line. In reference, that heart at 10 degrees Celsius, that heart is below the curve. Hopefully you can see that. That heart's definitely below. This situation, that would be an unsaturated solution as well. So it doesn't look like a good choice. Last one, find the KCl. Color, going dark red. KCl, find KCl. So again, what I'm using is zoom annotate. I don't know if you have the ability to do this, but if you do, I think it's relatively easy. If you don't, you can always mark it up with your doc. You could go to drawing. You could go to obviously scribble and color code it. KCl, that heart is below the curve. You can see that. Since that heart or that reference point is below the curve, that would be called unsaturated as well. So which one's saturated? It's on the curve. It's got to be choice B. B is the best answer for number 6. B, on the curve, saturated on the curve. So it still looks pretty intimidating because there's a lot going on this chart. But once you just go through what they're analyzing or asking to solve for, it's a little bit easier. I think question number 7 is probably a little easier as well. Number 6, best answer is going to be choice B. Any questions on that before I jump to number 7? It'll get easier with time. Let's try question 7. A solution containing 55 grams of NH4Cl and 100 grams of water is saturated at a temperature of what? So again, go through the question, highlight the important information. We have 55 grams. The substance is NH4Cl and 100 grams of water. And then it says saturated. Saturated on the curve. So you're going to have to know that. Saturated is on the curve. So find your substance. Let's go through it. Let's make sure it's 100 grams of water. All right. Big red flag. Water. 100 grams of water. Oh, yeah, we're good to go. There's no conversion that I'm going to have to do because it's already out of 100 grams of water. Checklist number 1 done. Maybe you want to find the curve next. NH4Cl. So find NH4Cl. NH4Cl, there it is. NH4Cl. Kind of a straight line. Next up, find 55 grams. 55 grams going yellow. 55 grams. Grams is going to be on the y-axis. 55 is in the middle. And we want to know what temperature, at what temperature is it going to be saturated. So you're looking for this intersection point between 55 grams and NH4. 55 grams and NH4. So if I'm following up, looks like it's going to be roughly there. So now I don't know if this is too much to do, but I don't really care about anything else on this curve besides, I'm going to highlight right there what's going to be left. So I don't care about anything else. I'm just going to do this one time, maybe another time too, but a couple times. Just so you know that nothing else is important besides the maroon, the red, and the yellow. So if I got rid of all this extra garbage here, or solubility curves, it's not that scary. It's not intimidating anymore if you just look at one curve at a time. That is all you really have to worry about. So yeah, I don't care about anything else but that right there. So I have a 55 grams of solute, and once I follow 55 grams over to NH4Cl, that right there didn't pop in there, but that right there is my reference point. It's on the curve. I want to know what temperature is it going to be saturated. So if I follow it on down, it looks like 57 is a solid answer for that. So 57 degrees Celsius is a point of saturation. If this question asks for a reference point with a point where my stars are, any point where my stars are, whatever it is, I don't care what point we're dealing with, any one of those stars is underneath the curve at that temperature. Any one of those stars would be the point of unsaturated. Under the curve, unsaturated. Any one of these points that are referring to the hearts where it's on the curve, it's going to be saturated or at equilibrium. And any one of the points where it's going to represent an X where it's above the curve, this is going to be super saturated in terms of NH4Cl. So on the curve, saturated. Under stars are unsaturated. And these X's are above, they're super saturated. So you have to find the reference point first. So the best answer for number 7 is going to be choice B. All right, let's try another one. 7 is B. Number 8. No, 8 we'll do later. I guess we'll do number 9. Number 9. Solution of NaNO3 contains 1 gram of solute dissolved in 100 grams of water. According to table D, should be G. At 50 degrees Celsius, the solution is considered to be what? Why don't you take a minute, try to think about this one, and try to figure out what the best answer is going to be. So I'm going to use the chart to the left because this one's too small. Find some reference point. I'll stop talking, think about it, and we'll come up with an answer. Okay, if you think you have an answer, please put it in the chat. Oh, thank you. Several answers, several B's and a C. Thank you. All right, so what I did, I highlighted the information from the text. We have water, it's 100 grams of water. We have the substance NaNO3, that's a blue font, that's a blue curve. I have 1 gram of water, 1 gram of the solute, which is a really low number. It's in yellow, it's approximately 1 gram. And I have a temperature of 50 degrees Celsius, which is in orange. I followed that all the way up to the top. My heart is going to be my reference point. So my heart, no, not my heart, the heart that I have here, the heart is right there. That's a reference point to this curve. That heart, is, if you follow it on up, is definitely below that curve. The curve, the heart's definitely below it. You can see that. So at that temperature, that heart is below the curve. It's under the curve, therefore it's going to be unsaturated. It's got to be unsaturated. How do you know if the point is dilute? Gotcha. How do you know if it's dilute or concentrated? So if it's under the curve, it's unsaturated, and that means you could put more particles in to dissolve. So more will dissolve. So this really just comes from knowledge from the notes a little bit. If it's under the curve, it's unsaturated, it's going to be diluted, diluted, dilute. Comes from the notes where it's dilute. There it is. Having low concentration. So there's not much of a solute in there. So more solute, relatively low concentration of solute. You could add more solute to the mixture. If something's concentrated, it's going to be probably super saturated, or it could be saturated. So either one of those would be an except or situation for that. Definition specifically. So just comes from the definitions. If something's going to be unsaturated, it's going to be diluted. You can add more solute. More sugar will dissolve to the Kool-Aid. If something is concentrated, it could be saturated or super saturated. Saturated is not going to be dilute ever. Unsaturated is not going to be concentrated. Something's unsaturated, you can add more solute. So those two terms go hand in hand. Those two terms go hand in hand as well. So would super saturated as well. So number 9, the best answer is going to be B for that one. Yes. Kind of drew me last. Unsaturated and dilute always go hand in hand. They're always going to be the exact same. If something's unsaturated, it's diluted. If something's saturated, it's going to be concentrated. There's a lot of solute there. If something's unsaturated, there's not much in the solution. So number 9, the best answer is going to be choice B. Let's go through at least one more. Check out number 10. Where are we for time? We have 4 minutes left. All right, please try out number 10. Please try number 10 out. Okay, please record the answer in the chat once you have an answer. So key thing here, I highlighted a couple things. I checked the water, make sure the water is at 100 grams, check mark, good, red font. I highlighted KClO3 in my blue, and then I won't always do this, but I guess I have the ability to do this on the docs. I think I'm actually teaching this lesson better now virtually than probably in person, because you could actually see exactly what I can get rid of or highlight a little bit better what I have here. So I got rid of the garbage, extra stuff, and now I'm focusing on just KClO3. I have a temperature of 40 degrees Celsius. I highlight that in yellow, and we're looking for the point of saturation. So point of saturation, put it in purple, saturates means on the line. At that temperature, where is the point of saturation? It's going to be at this intersection point. And a lot of you guys already put the answer. The intersection point here is going to be at roughly 16 grams. So what does that mean again? I could add 16, if I had a pitcher. Let me finish up with one last example. If I had a pitcher that had 100 grams of water in it, so I have 100 grams of water inside this pitcher. So let's wrap it up again. No sponge. So this pitcher has 100 grams of water in it, 100 milliliters of water. And for that 100 grams of water, I could add 16, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I could add 16 grams of KClO3 in there, and it will all dissolve. So once I add 16 grams of that and mix it up, it's going to dissolve, make a homogeneous solution. It's at equilibrium. Think of the sponge before. The sponge for saturated had no more room for any more particles. If I had 17 grams of KClO3, if I had one more gram of KClO3, that particle is not going to dissolve. It would be a super saturated solution. So if you add more, then that's not going to dissolve. So that is a wrap for today's class. It's 104. We'll pick up with those rest of these examples tomorrow for class. I wouldn't work on the exit pass yet. Well, I'll give you time tomorrow in class to finish it up as well. If you guys have any questions, feel free to hang out for a few minutes. But that's it for today. Have a good day. Make good decisions. Be kind to one another. See you guys. Have a good day. Bye, Nadina. See ya. See you, Kai. Bye, Faith. See you later.